Okay guys, let's solve this interesting integral here. The integral might appear very daunting, but in fact it is a very simple, straightforward type of integral that just requires a u-substitution. Okay, so let's see how to go about it. Okay, so looking at this kind of integral, the first thing we want to notice is that if you differentiate the denominator, you get the numerator. Okay, you can check the derivative. The derivative of a constant is 0, but the derivative of tan x is actually 1 plus tan squared of x. You can check that derivative from our YouTube channel. You'll see where I've shown that the derivative of tan x is 1 plus tan squared of x. We've shown that from first principle. Okay, so we're saying that if you look at this, you can see that if we differentiate the denominator, we get the numerator. In other words, this is the case of a function and its derivative. And so, if we want to integrate this, we need to use u-substitution. So whenever you can show that the integral contains a function and its derivative, either in quotient, that is the derivative at the top and the function at the bottom, or the derivative and the function side by side as a product, if you can see that, then the integral can be easily solved by a method of u-substitution. Okay, and so using u-substitution, we will let the denominator there be represented by letter u. Okay, so let u be 6 tan of x, and if you differentiate this, du by dx is just going to be 1 plus tan squared of x, and 1 plus tan squared of x from Pythagorean identities of trigonometry is the same thing as sec squared of x. Okay, and so dy by dx, then if we let that be u, then dy by dx is going to be 1 plus tan squared of x, which is equivalent to sec squared of x. What I'm saying is, I notice that if I differentiate this denominator here, so d by dx of 6 plus tan of x, this gives me the derivative of a constant is of course 0, but the derivative of tan x is 1 plus tan squared of x. Please go to my videos on Elimika, Dunia, and you'll find under topic 5 playlist, I have proved some derivatives such as e power x, a power x, tan of x, sine x, and so on. Some of the common derivatives, we have proved that using first principle, differentiation from first principle. Okay, and so this is this, and we know this is comes from the Pythagorean identity sine squared x plus cos squared x equals 1, which can be used to show that this is the same as sec squared of x. So in fact, the derivative of the denominator is the numerator. Okay, the dx can come here, so du is equal to du becomes equal to sec squared of x dx, and so I can remove sec squared of x dx, all this, and replace with du like that. And that means that because I'm using the u-substitution, now I have the integral of, in place of sec squared of x dx, I will just put du, okay, because du is sec squared of x dx like that, and the denominator is u. We are effectively done, other than integrating 1 over u du. So our answer then, our preliminary answer is ln of u, and of course plus c, because we do not have the limits of integration there. Okay, and so all we have to do now is put back our value of u that we had substituted. Remember, we said let 6 plus tan x be equal to u. So I'm simply going to put that back there, and we conclude that the integral of that expression is just going to be ln of 6 plus tan x plus c, like that. Okay, hopefully you understood. If you like the video, please scan directly this code to get to our YouTube channel. Okay, consider subscribing to the channel as well. Thank you very much. I hope you enjoyed that. I'll see you in the next video.